Before I proceed with my presentation, I would like to thank the conference organizers, GSTF, for inviting me to present this keynote address. Secondly, this one, I actually collaborated with my student sitting here, Sripati, Bhargav Sripati. So he's doing his PhD under my supervision. Now in my presentation, I will start with a very basic understanding of what is energy efficiency. I'm sure all of you got some idea what is energy efficiency means, and then discuss the scope of energy efficiency in chemical processes. This talk is more towards the chemical processes and chemical engineering. Let me get some idea. How many of you are chemical engineers? Can you raise your hands?
Do you count chemists?
Okay, all right, so good. We do have some chemists, I know the numbers, so good. I'll keep this one simple for the benefit of non-chemical engineers, so I won't go into too many details of the computational aspects, the calculation aspects. Then after the introduction on energy efficiency, I will discuss the heat exchange network retrofitting, briefly cover what are the methods that are being developed, that are being used for the heat exchange network retrofitting. I will also cover one case study, that will be the major part of the heat exchange network retrofitting, present the results, make some discussion. As part of that, I'll be using the multi-objective optimization. I'll introduce that also. Finally, I will end up my presentation with a short summary. So what is energy efficiency? I'm sure you all have some rough idea. So essentially, trying to make more out of the energy that is available to us. So same services for less energy input, etc. What is the benefits of this? Certainly by having the more energy efficiency, improving the energy efficiency, we can limit the growth of the energy consumption. As you know, the countries are developing. As the countries are developing, the economic development means there will be more energy requirements. So hopefully with the better energy efficiency, increased energy efficiency, we can reduce the energy requirements. One simple example from our day-to-day life, you can see that the benefits of fluorescent bulb uses, fluorescent bulb compared to the incandescent bulb. Nowadays they got more energy efficient bulbs too. Energy efficiency, one aspect of this energy pyramid, you see the three things. Energy conservation, trying to use less energy, and when we use energy, use it more efficiently. And the third one is using more renewable energy. What are the benefits of this? I'm sure you understand these things. One is less CO2 emissions, or in other words, reduced global warming. And if you use less energy, that will also means less operating cost. So for the electricity, for other things. Oh, yes, we would like to have highly energy efficient processes, the units, but what is limiting? A couple of factors are limiting. One, if you want to go for higher energy efficiency, you may have to spend more. That's the capital cost part, increased capital cost. Second one, the energy prices are fluctuating. If the fuel cost is very low, then there is no incentive for the people to go for highly energy efficient processes. The third one, sometimes the energy efficiency means, more energy efficiency means you need to use new technology. And with the new technology means people, the companies are not familiar with the technology, and they're hesitant to try out the new technology. So lack of experience is another one. Let's focus on the energy efficiency in the chemical processes. There are many operations with chemical processes, chemical industries, which involves the reaction and separation. And these operations require either heating or cooling, because those operations require certain temperatures for them. There are also many other operations. For example, the compressing a gas stream, or mixing or size reduction, which requires energy. So in all these things, there is a scope to improve the energy efficiency of each and every operation. Another aspect is there are already many chemical plants which were constructed in the past, they have been operating right now. Numerous plants are there like that. The question is, are they energy efficient? Can we improve on them? So that is where the retrofitting comes into picture. Making the modifications to the existing plants, existing processes, so that you improve the energy efficiency. So I focus now on the heat exchanger networks. What is this heat exchanger network? So this one is a typical chemical processes. So we start with a feed, which is entering at roughly room temperature, room conditions. We put through the certain operations and produce the final product, which is somewhere here. And the operations involve, as I said, the reactor at some high temperature, some separation systems, again requiring certain temperature for their operation. So as part of this, we need to do some of this heat exchange here. You see the heat exchangers here. You got 1, 2, 3, 4, 5, 6, 7 of them. And you see the streams, the process streams. These streams in the red color, these are the streams which have to be cooled. So we refer them as a hot streams. And there are streams which have to be heated up to a higher temperature. So these are the one with the blue color. So these are the cold streams. Okay? So this kind of a process is certainly energy intensive. So there is a scope to reduce the utilities. Utilities meaning, if you look at this heater, it requires the external energy input. It could be in the form of steam or some other source of heat. So this is where the utilities are being consumed. If you want to cool this one or this one, we need cooling water. Again, we require energy to produce the cooling water to supply. So there is a scope to reduce the utilities. Now, what is the heat exchanger network? So the heat exchanger network consists of these exchanges and the coolers, the heaters. These are represented in this grid diagram, just focusing on the heat exchange and not on other operations. You see the hot streams shown in the red color, goes from the left to the right, and the temperature is decreasing. And you see the cold streams, which are here, the temperature are increasing. And you see the energy recovery and reuse through these exchanges 1, 2, 3. That means we are recovering the energy from the hot stream, and that one is being used for the cold streams over here. Apart from that, there is the heaters and the coolers. So this one is referred as the heat exchanger network in the chemical industries. Well, heat exchanger networks is also there, not just in the chemical industry, in something closer to us. For example, in the cars, there is a heat exchanger network. So they try to improve the efficiency, energy efficiency of the cars. The improvement is only a few percentage points, 2%, 3%, but it's still significant because there are so many cars being produced and being used. So let's come to the heat exchanger network retrofitting. So what kind of changes can we make to the existing network? So some of the things are listed here. You can add the heat transfer area to the existing heat exchangers. You can also improve the heat transfer characteristics, the heat transfer enhancements. Both these things means within the existing equipment, you can achieve greater heat transfer from one stream to another stream. You can also bring in a new heat exchangers. You can you can buy and install the new exchanger. You can also do some resequencing of existing exchanges. And also there's one more repiping. There's a subtle difference between the resequencing and repiping. It's indicated by the one in the bracket. In this one, the process streams in that exchanger is not changing. So it's just changing the position on those streams. This one means the streams in the exchanger are changing according to certain way. There are many things one can do. All this one means it requires some kind of optimization to find out what is the best combination of doing these changes. Now, in the heat exchanger network retrofitting, there is a considerable research focusing on the retrofitting. There is also a lot more research on the heat exchanger network synthesis. What is the difference between retrofitting and synthesis? Synthesis refers to designing a new plant or grassroots design, not talking about the existing one, making modifications. So with the new design, you got more freedom, less constraints, so easier to do. Similarly, the research on that is relatively easier, so they focused on that in the beginning. Now the focus is on more on the retrofitting. So this graph, the slide shows the number of journal papers published on the ejection network retrofitting over the last 20 years period. Each bar refers to 3 years, except the last one. That's just the last year one. So you can see increasing trend of research in the retrofitting, ejection network retrofitting. So if I look at the research on this retrofitting, there are two classes of methods, broadly two classes of methods. One is based on the so-called pinch analysis, based on the fundamental principles in thermodynamics and heat transfer. So they use the basic principles and also some heuristics. Heuristics are the experience-based guidelines. They also bring in some new things, composite curves, finding the targets before you actually think of a solution. You start with a problem, then you go through finding the target, what is the best you can achieve, and then go on thinking of the solution. The second group of methods is this optimization-based methods. So they require formulating an optimization problem, meaning you need to define an objective function. You need to identify what are the decision variables. You also need to list down what are the constraints. So that will be the optimization problem. Once you formulate, then the next step will be to think to solve it. Solution for this optimization problem cannot be done analytically. You have to go for some numerical methods. That's where the optimization methods come. There are a number of methods. One can define, classify them as deterministic methods. Second group is the stochastic, also known as meta-heuristic methods. So these are the two groups of methods. And these methods can be for a single objective optimization, that's for the global optimization, or could be for the multiple objective cases. So we'll be focusing on the multi-objective optimization. Now this slide shows the methods for the pinch analysis-based methods and the optimization-based methods over the last 20 years. What are the focus, what are the topics within these methods that was proposed or developed over the last 20 years period. So the top one refers to the pinch analysis-based methods. This one for the optimization-based methods. If you look at the optimization-based methods, they started with some kind of a two-stage approach, slowly moved to a single stage type, and then this one refers to the mixed integer nonlinear programming based methods. And the superscripts which you see are really the citations which are given in our paper, in our recent paper here. And if I go on to this one, this over here you see a one-step approach using the stochastic methods like genetic algorithms for the retrofitting. Now let me say a few words about the multi-objective optimization. In this case, we're looking at two objectives, not just one objective. For example, it could be minimizing this the function f1 here, certain objective. The second one could be this one. So there are two objectives. Often these two objectives are conflicting. That means the solutions which you can think of, they will be in this form. The red diamonds, there are many solutions, and these solutions satisfy your constraints. But in terms of the optimality, they are not better one, they are inferior one, or they are dominated by others. The optimal solutions are the one in the green. This is the one. These are the optimal solutions. You can see that there are many optimal solutions, not just one. What is the reason? There is a conflict. If you try to minimize this one, this F2 tends to increase. If you minimize this F2, F1 tends to increase. Okay? So this is the type of situations we face. So in the multi-objective optimization, our interest is to find these green circles. These solutions are known as Pareto optimal front. As I said, there are many optimal solutions there. So what is the benefit of having these optimal solutions? So first of all, the optimal front shows the quantitative trade-off between the two objectives, not simply qualitative. Qualitatively, perhaps you know these two are conflicting, one goes up, the other one goes down like that. But this one gives you a quantitative idea. It also shows you the optimal values or trends of the decision variables. This one is not shown here. What I'm showing here is only in the objective function space, not in the decision variable space. But if you do the multi-objective optimization, yes, you also get this optimal values of the decision variables. Now, with all this one, we got a greater insight for selecting one of the solutions for use for implementation. So that's the benefit of multi-objective optimization. So with that, let me move on to the case study. This case study, there are a number of streams, H1 to H10. These are the hot streams. There are also a number of cold streams, C1 to C5. And you see the number of heat exchanges numbered here, starting with 1, let me see, 2, then 3, 4, etc. The maximum number, or the total number of heat exchanges is this one, 17 heat exchanges. Each of them has got certain surface area in that. So the values are shown here. Now we want to start with this one. This is the existing heat exchange network, perhaps in some plant. How can we improve on this one? That is what we are facing. So for this, we formulate the objective functions. There are two objective functions. One, the cost of retrofit. You don't want to spend too much money on retrofitting, on changing. At the same time, you want to minimize the utility cost, the cost of utility. This cost of utility is really the energy which you are using. You want to minimize the energy. The decision variables, these are the possible changes that can be implemented. Remember the area addition, the new exchanges, repiping, resequencing, all those things. For this one, we use the MATLAB. There is a nice program. It's effective, it's a reliable program known as the NGPM, developed by another group. And this program is based on a genetic algorithm for multi-objective optimization. Now, what I'm showing is very briefly on the optimization algorithm. So what you see is the algorithm here. This is based on, as I said, genetic algorithm. That means it's using a population. It's also using some genetic operations like a mutation, crossover, selection, and then going through a number of generations. But this is the program, that NGPM program. That alone is not sufficient. We need to develop our own program for the heat exchange network model. So this is our heat exchange network model calculations. The two, of course, interact. You see here, this is where the HEN model is being called. So it has to do these calculations and compute the objective functions. There are also somewhere here also. So we use this program. We solve this particular case study. So what are the results we got? Before that, some characteristics of this problem. There are 15 continuous variables. There are many discrete variables or integer variables. So continuous variables are for the exchanger area addition. This one is for making the changes, the repiping, resequencing, even the where to put the new heat exchanger. So all those things are in these discrete variables. The algorithm parameters, we were quite ambitious. We are using a large population size just to make sure we are getting good solutions or the best solutions. Maximum number of generations is also quite large. We use a MATLAB with a parallel computing toolbox. We run this program on the desktop computer, a typical desktop computer, nothing fancy. Computational time somewhat large. So if you take for 500 generations, it takes 2 hours. If you go for 2000 generations, it takes about 7 hours. Now this figure shows the optimization results. You see the objective cost of retrofit. This is the utility cost. sorry. As you can see, as the cost of retrofit increases, the utility cost decreases. So this information is again useful to the practicing engineer, the company management. So how much money are you spending? What is the benefit you are getting? And the results are shown here at different generations. The blue plus points are the generation 500. The green is the generation 1000. Black one is 1500. The red one is for 2000 generations. If you see these results, you probably require just about 1500 or 1000 generations to get good results. If you want to get even better, then you have to choose a large number of generations. Now, after those solutions which we got, I'm going to discuss one particular solution. We chose this one, this particular one. Why did we choose? We see that this one, the utility cost is on the highest side. There is a sudden decrease here. So we think this is a good solution. We don't spend too much time, we don't spend too much money, but we get a greater savings. Now for this particular solution, this is what the solution looks like. The exchanger areas are shown here. The one you see in the bracket, these are the changes, whether the area is added or decreased. So many of the changes are quite small. Let me give you some specific things. So there are two exchanges, this 16 and 17. The area addition is significant. The remaining, the area changes are not so much. So one can perhaps manage without making those changes. There is one new heat exchanger placed over here. There is also one exchanger which was shifted on the same streams. Instead of at a lower temperatures, it has been moved to the higher temperatures. And there are a number of repiping. That means these exchanges which you see in the blue shading, they have been moved from the certain streams to another set of streams. With these changes, the benefits is something like this. You spend about $253,000 for making the changes. And the advantage, you reduce the utility cost by $1.7 million. So you can see the benefit immediately. In terms of the energy, the utilities, the hot utilities is reduced by 12%, the cold utilities by 20%. One can choose many other solutions on that Pareto optimal front. What you are seeing is some of them. So one can choose either this one, or this, or like this. In this one, as you see, the cost of retrofit is increasing. The utility cost savings is increasing. And the payback period, if you calculate, is a few months only. So you're looking at 2 to 5 months time. I want to emphasize one point. If you look at these two solutions, in terms of the cost of retrofit is similar, utility cost is similar, but the changes to be made is slightly different. So you see here, repiping, you don't have to do 8, you can do only in 7. But the resequencing, you have to do more. Sometimes this set of changes could be easier compared to this one. So one can analyze this, the engineer can analyze this and choose one of the solutions, one of the good solutions. In terms of the Ejection network retrofitting, the studies are going on. What I'm listing is just a recent studies. So this one is from a group in Manchester University. So they are studying this heat transfer intensification using the heat transfer enhancement of things. We're also doing the research. So this one is using the multi-objective optimization for the Ejection network retrofitting. We've got another one, very recent one. So this one is looking at the process streams whose heat capacity, the specific heat, is not constant, is a function of temperature. So we're looking at the variable heat capacity situations. Again, how do we do this heat exchanger network retrofitting? So with that, let me summarize my presentation part. So we all understand, we all agree that energy efficiency is very important. We should try to improve it as much as we can. Heat exchanger networks are important in the chemical processes, and improving the energy efficiency is certainly also crucial. So we can use a multi-objective optimization for this ejection network retrofitting, and with that you get a more understanding of the trade-off in the objectives. You will also have some idea about the decision variables and their values. If I look at the case study, it's very promising. As I said, the payback period is only few months, and you can reduce the utilities by about 20%. So we feel the multi-objective optimization is useful not only for the ejection network retrofitting, but for a complete chemical process retrofitting, revamping. In fact, it's also useful in the chemistry. We don't see much work in the chemistry area for the multi-objective optimization. With that, thank you very much for your attention.